Good evening. We need to hurry up so that my battery doesn't run out before I run out of content. Which leads me to the topic robots. This talk is about what we need to consider when developing rules and regulations for robots and for autonomous systems and other complex technological entities that are not manageable by a normal way of managing risky technology. We start with the three laws thanks, Kit. That Asimov stated in his novels. They should be universally known. They say a robot should not harm a human being, either actively or inactively. It should follow orders and it should preserve existence. These rules are fine as subjects for novels, but they're unfortunately very impractical when it comes to real-world systems. There has been a very nice illustration to that. These rules do not include the option of malicious intent. So no one can, under these rules, develop systems that hold up to malicious users, to malicious builders, to malicious people trying to influence the systems. So we need to conclude robots are risky. So there is no way denying that. When we look at Asimov's laws, they have different statements in them, like injure, harm, what's a human, orders, protect. So there's existence. What's that? So there's no means of knowing for a robot what does it mean to harm a human. So what's the meaning of protect? So is it, I don't know, just standing here? So currently most robotic systems, if they don't know what to do, they just remain standing still. So if you look at, for instance, the videos of the DARPA challenge, which was the big trial out for having automated cars driving around in a simulated urban environment, what they basically did is they had 15 teams and they had automated cars that should fulfill a number of tasks. And they had stunt drivers in actual cars simulating human traffic. And they wanted to show that these cars can drive around in the city without harming too many humans. And actually the number of accidents was surprisingly low compared to 2 years before, when it was a non-urban trial where they drove around the desert near Las Vegas. And so it was relatively cool. So they had these cars full of sensors and everything, trying to drive around. And when these cars were out of options, basically not knowing what the environment was or not being able to conclude what they should do, they were just sitting there waving a red flag and saying, okay, I don't know what to do. So the problem is there's no real artificial intelligence on the horizon. So artificial intelligence is more or less like fusion power. It's always 15 years in the future, always, at any given point in time. So, and it has been that way since the 60s. It's always 15, maybe 20 years until we have real AI. And it will be really cool. But what we have is increasingly complex software. So the systems that we are building today that are running actual machines like industrial components, even normal personal computers or automation systems, semi-autonomous machines that are driving around in factories. The software is getting increasingly complex. It is getting so complex that you're not really doing any systems engineering in the conventional sense on them anymore, but they behave. So if you talk to operators of really complex machinery, they tend to personalize the software that they need to work with. We come to that later in detail. This kind of software caused already death and injury. What we have here is a satellite picture of California in the August 14, 2003. What you see here is California, and it's dark. because they had blackouts. And the latest postmortem I have read about it was these blackouts could have been prevented to a large scale if the reliance on automated systems was not so total that the functioning of these systems was taken as a given. In other words, the systems failed and the human operators, the few that remained there, got too much input to parse. So a cascading failure in an energy network is something that no human being can conceivably stop because there are way too many options. So it's the same basically with the nuclear power station. They try to skim down the options that an operator has in a nuclear power station by using multiple automated systems so that he can maybe understand what's happening, but in full-scale power system, that's not possible. Plus, almost all modern software is buggy. And above a certain complexity level, it's not even deterministic anymore. So if you look at what is happening in the field of what's called artificial intelligence in computer science, that's neural networks, that's stuff like motivation-based learning. And these are more or less self-evolving systems. They are not intelligent, but they are not deterministic anymore, and they are not predictable anymore. So you cannot really predict what these things will do in a given situation. You can just have certain convictions about what they should do. And so the point of software is something deterministic, and we can understand what the system does is long past gone. The graphic behind the text here is the Windows 32 call graph for system functions. And who here would think that Windows 32 is a deterministic software? I see no hands. Okay, there is the option of saying these systems could be legal entities. This is actually being debated in the scientific literature, saying if a system has certain characteristics, that it knows about the environment, has rules how to decide about its environment and what it should do or should not do, has something like a computerized moral or ethic framework on what to do and not to do, then it should maybe get the status of a legal entity that earns its own money and is therefore being able to pay its own insurance. Which I find a fascinating construct of logic, but the problem is this also doesn't really hold up in reality. So if you have such a system and somebody's building it, it thinks, okay, this is not an entity but a machine that I own, and this is what we're thinking currently. So, but at least it's being discussed. What we have today is not really fully automated robots, but lethally armed remote presence machines. So these things that we have here is a little tank that has a machine gun, a couple of cameras, lots of wireless stuff. It has actors, it can mount an arm, lots of batteries in it. And these things are actually deployed in the battlefields today. So it's not future, it's just the stuff that is from a product catalog that you can actually order as a military today. These things have very, very limited onboard intelligence, but they can theoretically operate beyond visual range. So we're having normally the definition, okay, a remote-controlled machine is something that is operating behind there in the corner because I don't want to go near the bomb. But actually what we have today is UAVs that are flying around the world controlled from somewhere in Kentucky. And these things have onboard intelligence that at least makes it possible that they fly to a certain corner of the world and fire a Hellfire missile without somebody having really tight control but saying, okay, go there, okay, looks like a target, fire. So there is a transition from remote presence to autonomous systems. And that's a very fascinating transition. Somebody has written in, more or less in reply to Asimov laws. It's basically saying a robot will not will not attack government personnel, but everybody else. And it will, of course, obey orders. And it's goddamn expensive, so better protect itself. I found these laws actually more realistic than Asimov laws. The author is a British science fiction writer. To get another glimpse of what is happening today, we have here a video from a drone in Iraq that is getting a bit out of control. So now it's in auto land mode, and it's landing. The face of that guy is really priceless. So, what we have here is somebody who has really, really high confidence in software. And so that brings us to the very interesting question. So let's assume somebody put in the wrong coordinates and and he would be actually wiping the floor with that guy. Who would be responsible? Is it the maker of the robot, the writer of the software, the guy that happens to be 10 centimeters too tall? So, but these are the questions that we have. So this could be not an industrial robot with some robot engineers having fun, which it is actually in this case. But that could be a piece of entertainment software tied to a physical interaction device. So we're moving into a realm that has increasingly complex questions. If we want to invent regulation or rules, we should define goals. Rule number one, we should try to reduce the number of victims. Of course, we want to save money. Rules and regulations should be developed in practice so that they are actually practical and not just stupid rules that somebody developed on the green board. We want to prevent stupid panics, like robot armies will roll over the streets and eat us all. And we want actually meaningful and realistic regulations. So what could be elements? This is something that is not actually a robot, but a remote-controlled plane. So that plane is also getting a little bit out of control in just a second. And it's not stopping. It's just simply not stopping. So now we imagine that thing landing in a kindergarten. This would cause a stupid panic. Yeah, it's a bit lengthy. Chopping up little lambs. Now it's dead, Jim. So let's take a look at what the current regulations model for risky technology are. There is already lots of risky technology around, so the question is, can we learn something from that? We have the Anglo-Saxon approach. If it can be ensured, it should be okay. Actually, while researching this talk, I learned something. You probably have seen this logo on a lot of PCBs, that one here. Does anybody know what it stands for? It's for a registered part for and recognized part for the Underwriters Laboratory, which is the logo on the left side. The Underwriters Laboratory is basically an entity in the United States that says, okay, we are analyzing electrical and electronic components and see if they are safe. And when we have them analyze them, then they can be insured. And similar models are working in other countries. But this approach is basically only industry-driven. It's basically saying the industry says, if we can determine the risk, we can determine